So with that, let me kick things off. So I introduce our first speaker today. So Professor Gentaro Watanabe from Zhejiang University, and so he's going to talk to us about universal bounds for fluctuations in heat engines. So take it away, Professor Watanabe.
Thank you, Sai, and I would like to thank organizer for giving me this nice opportunity to present our work. So that this work is about the fluctuations of the small heat engines, and then this work has been done in collaboration with Dr. Kosuke. He was a former postdoc of our group, and now he's moved to the Osaka University as a postdoc. And then my student, PhD student, Mr. Chao Jian. So this work has already been available in the archive. So if you are interested in, please have a look at. So this is the content of my talk. First, I'd like to briefly introduce the system. We are considering the so-called stochastic heat engine, which is a classical small heat engine. Hopefully, this also interest for you, those who are working on the quantum system. But my talk is mainly the classical system. Then I would like to briefly explain the important properties of the quasi-static process for small systems. And then I will explain our result. So that we found the universal relations between the work and heat fluctuations. And then we have also shown the universal bounds for these fluctuations. And then we briefly mentioned the applications of our results. Okay, so the heat engine is originally this type of macroscopic device. However, technological development allows us to downsize this heat engine into the very small scale. So here, small means number of the degrees of freedom is small. So nowadays people can realize the heat engine using the small system as a working substance. For example, this example is a heat engine made of the with a working substance of the single colloidal particle trapped in the optical tweezer. Also, people can realize a heat engine using the even single atom, like this example, or quantum system. So the present work, we consider the stochastic heat engines. So the stochastic heat engines are the heat engine with working substance for using the small classical system as a working substance. For example, the colloidal particle or a macromolecule in the trap. So this is a kind of schematic picture of the stochastic heat engine setup. So that there is a colloidal particle trapped in the optical potential. And then this control parameter is, the trap strength, oscillator strength, for example. And then the surrounded water works as a heat bath of this colloidal particle. And then this colloidal particle is a working substance. In this situation, the system is governed by the stochastic processes because this colloidal particle gets random forces around the water molecule. Therefore, for example, energy and the work and the heat, these kind of quantities are random variables. So the important issue for the stochastic heat engine is as follows. Because the system is small, therefore, fluctuations is not negligible anymore. Therefore, to characterize the performance of the engine, it is also important to go beyond the mean value. So far, typical measure for the characterizing the heat engine is the efficiency or power. These are based on the average quantity. However, we would like to go beyond by characterizing the heat engine using the higher order statistical quantities. So our strategy is basically focusing on the quasi-static limit and then try to obtain some universal relation. Actually, the quasi-static limit is not so unrealistic situation for the small heat engines because the number of the degree of freedom is small and the phase space structure is very simple. Therefore, many processes involved in the stochastic heat engine, something like heat transfer from the heat bath to the working substance, or say processes surrounding all the possible phase space in the say system, this kind of time scale is actually the microscopic time scale quite often. Therefore, the quasi-static limit can be effectively reached within the time scale much shorter than the macroscopic one. And actually, the quasi-static limit is relevant to the experiment, which has been realized, for example, this experiment by Martinez et al. Actually, there is some important quantity which is commonly used. This quantity is a so-called fluctuating efficiency, namely the efficiency as a random variable. So which is defined like this. Here, W and the QH is the work and the heat, but this is still a random variable. It's not the average quantity. And then this eta is defined by these two random variables. Therefore, this eta is also the random variable. However, this is quite interesting quantity, but this distribution of the eta hat is highly non-trivial. This is interesting. However, due to this non-triviality, it is rather difficult to reduce the general scenario to narrow the distribution. And also, as far as I know, the universal property of the eta is still unknown for general cases. So that we focus on other type of quantity, basically the fluctuation, ratio of the work fluctuation and the heat fluctuation. So that here we consider these two quantities, basically the higher order central moment of the work and the heat, and then consider this ratio. And then we found that these quantities actually show the universal relation for the Carnot engines. So that this eta n is defined by the ratio between the central moment of the work and the central moment of the heat input from the hot heat bath. And then this is equals to the Carnot efficiency to the power of n. This psi2 is defined by the second order, variance of the work divided by the variance of the total heat input. And then it has this relation for the Carnot engine, Carnot cycle. So that this is universal, namely that this ratio, quantity only depends on the ratio between the Tc over Th. Tc and Th is the temperatures of the hot heat bath and the cold heat bath. So that this is one of our main results. And then we have also shown that Carnot cycle provides a maximum bound for these quantities. More precisely, we consider the quasi-static cycle, namely the cycle consists of all the quasi-static processes. And then among these class of the cycle, Carnot cycle provides a maximum bound for these quantities. Namely, this psi2, it is maximum actually for any quasi-static cycle. On the other hand, this eta2, it is maximum for the Carnot cycle. It is maximum for the quasi-static cycle, all of whose adiabatic expansion stroke are preceded by the stroke with the hot bath. But this is actually quite necessary. Oh, yeah.
So there is a question by Jay Dong. Please go ahead.
So excuse me. So can you please explain the difference between these two quantity eta and psi?
Oh, so the eta is a ratio between the work fluctuation divided by the heat fluctuation, but the heat input from the hot heat bath. Psi denominator is different. In the case of the psi, the denominator is a heat input, total heat input. So there is a contribution from the heat output towards the cold heat bath.
Okay, thank you.
Yeah. So this eta is maximum, and for some specific class of the quasi-static cycle, such that adiabatic expansion strokes are preceded by the stroke with the hot heat bath. But this is quite a natural situation because after heating up by hot heat bath, then we have the adiabatic expansion. After, say, cool down by the cold heat bath, we have the adiabatic compression. For example, various typical type of the engine like Otto cycle, Brayton cycle, Stirling cycle. Actually, they fall in this class of the quasi-static, class of the cycles. Okay, so later on, from now on, I would like to explain our result in detail. So actually the Carnot cycle consists of the, say, quasi-static isothermal processes and the quasi-static adiabatic processes. So first, I would like to explain the quasi-static isothermal process, and then there is some important properties. So this figure shows a typical schematic situation of the quasi-static or isothermal expansion of the stochastic heat engine. So the working substance is immersed in the heat bath, which is given by the water molecule. And then I expand this, say, potential slowly, quasi-statically. In this process, the working substance, this colloidal particle, actually is subject to the random force by the heat bath. Therefore, work through this isothermal stroke is actually stochastic. So here, I show the position of the, say, colloidal particle as a function of time. And then each line, zigzag line, corresponds to the single sample path. So that if I take one realization, I have this one, and then I can obtain the work for this trajectory based on this say, integrating the power with respect to time. Of course, if I take another realization, path gamma is different, and then this work value is different. Then what we want to discuss is the statistical quantity of this work. For example, the work, this random variable for each trajectory weighted by the PDF for the trajectory gamma, and then performs the path integral. So this is the average of the work, and then this is the second moment of the work. And then we want to consider, for example, mean value of the work and the variance of the work like this. And then the important quantity, important property for the quasi-static isothermal process is as follows. Actually, the fluctuation of the work through the isothermal process becomes negligible in the quasi-static limit. More precisely, the variance of the work through the quasi-static isothermal process decreases as a function, as a 1 over tau, and the tau is the duration of the process. So if I take tau infinity, then the variance goes to 0, and then the work becomes deterministic, essentially. The physical reason of this property is as follows. Actually, there is no long-time correlation in the variation of the force exerted by the working substance. Therefore, if I take this duration of the process much bigger than the correlation time, then the fluctuation cancel out. And then if I take tau infinity, then the system thoroughly takes all the possible microscopic states at each instant value of the external parameter. Therefore, we have the law of large numbers, and then work becomes deterministic. So as a result, the work as a random variable actually equals to the work, average value of the work. So this is one of the important property of the work in the quasi-static isothermal process.
So we have another quick question.
Yeah.
John Greg, go ahead, please.
Yeah, sorry to interrupt. Can you go back to the so like in the usual law of large number things, we get this like Gaussian distribution of the random variables, right? And I think in that case, usually this variance increase as the time, but like the squared of the average increases like time squared. So we get
so the variance decreases by the number of the realization.
Oh, so
1 over square root of n. If I make many realization, and then the variance decreases by 1 over square root of n. So the time actually corresponds to the number of realization, something like that. So that we try to, if you say play with dice, and then I do the dice for many times. So that then this number, the variance becomes smaller and smaller by increasing the number of the realization.
Also, you're saying that is going even smaller, like even without dividing by the average.
Yeah.
Okay, thank you.
So this variance is a relative variance. So that after divided by average, then it will be 1 over square root of n scaling.
So it
relative
is
variance,
divided by average.
Relative variance decreases according to this 1 over square root of n.
Oh yeah, thank you. I get it now. Thanks.
So that now I want to explain the important property of the adiabatic processes. So unlike a macroscopic system, actually in the case of the small system, system does not necessarily relax into the equilibrium state during the quasi-static adiabatic process. So the final state of the quasi-static adiabatic stroke does not follow the canonical distribution in general. So that if please, here I show the PV diagram of the Carnot cycle. And then there is a quasi-static isothermal stroke, 0 to 1. And then please focus on the quasi-static adiabatic expansion from 1 to 2. So that this 1 minus is just before ending the isothermal process. Therefore, the state here is a canonical distribution, canonical state. And then 1 plus is after finishing the isothermal stroke. Then we remove the contact from the heat bath, and then my system takes some microstate following the canonical distribution. And then starting from this microstate, I perform the isolated evolution. And then I go to the, node 2. This, and then 2 minus is just before the end of the adiabatic stroke, so that I have the microstate adiabatically evolved from the state 1 to 2. But this distribution is not necessarily equal to the canonical distribution for this parameter and this temperature. Therefore, to be reversible between this 2 minus and 2 plus, the final state of the quasi-static adiabatic stroke should follow the canonical distribution of the subsequent quasi-static isothermal stroke. Otherwise, there is an irreversible heat flow between the, working substance heat bath at this point. So that due to this irreversibility, we need to impose the condition to guarantee the reversibility. So that this is a condition for the reversibility. So the necessary and sufficient condition such that canonical ensemble for a given temperature T2, final temperature T2, as some parameter lambda 2 is consistent with the final state of the quasi-static adiabatic stroke is this condition up to constant. So here, E1, E2 is an energy as a random variable for the initial and the final point of the adiabatic stroke. And the T1 and the T2 is a temperature of the initial, beginning and the end of the adiabatic stroke. Okay. If this condition satisfied, then we can remove this irreversibility. So to consider to construct the Carnot cycle, we limit ourselves for some specific class of the working substance. Namely, such kind of lambda 2 can be found for any value of the initial parameter and then the heat baths, temperature of the heat baths. Namely, Carnot cycle can be formed for an arbitrary choice of the hot and cold heat bath temperature and the arbitrary lambda at starting point of the quasi-static adiabatic stroke. Yeah, there is a question.
Yeah, there's a question.
So I have one question. Does your adiabatic process is performed with heat bath or without heat bath?
Without heat bath. Adiabatic process in my word is there is no thermal contact with the heat bath. Therefore, the system is isolated.
Thanks. And I missed one point. So why is the lambda? Is it protocol?
Sorry, I mean, lambda is a parameter. For example, in the case of the piston, and then the position of the piston is a lambda. So that in this case, volume corresponds to the lambda. Lambda is a mechanical parameter which can be controlled externally.
Thanks.
Yeah. So we constrain ourselves such that we can construct the Carnot cycle for any choice of the temperatures of the hot heat bath and cold heat bath, and then any starting point of the adiabatic strokes. So this sounds a bit restrictive. However, the typical setting of the stochastic heat engine actually fall into this class of the working substance. For example, the single particle trapped in the harmonic oscillator potential or a single particle trapped in the box potential, actually they fall into this class of the working substance. Actually, the sufficient condition to be this class of the working substance is number of states can be written in this form. The lambda is a parameter, and then the E is the energy of the energy. So the number of states inside this energy shell can be written in this way. Then this is sufficient condition to guarantee this working substance. And then the typical setting actually fall into this class. Okay. So that here I just show that T lambda plane of the Carnot cycle. We have the two adiabatic strokes from 0 to 1 and the 2 to 3. Isothermal stroke from 0 to 1 and the 2 from 2 to 3. And then two isothermal adiabatic stroke from the 1 to 2 and the 3 to 4. So now I would like to briefly explain how we can get the universal relation of the eta n. Eta n is defined by this. So the n or the central moment of the work, and then also the central moment of the heat input from the hot heat bath. Let's consider the stroke from 0 to 1. This is isothermal stroke, quasi-static isothermal stroke. According to the first law, QH, this is random variable, is given like this. Energy difference plus work, according to the first law. However, fluctuation of the W 0 to 1 is negligible because we consider the quasi-static isothermal stroke. Therefore, this becomes deterministic. And then for the heat fluctuation for, say, this QH, only E1 and the E0 contribute. This W 0 to 1 doesn't contribute. Sorry. And then next, we want to consider the work fluctuation. So the work through the whole cycle, we have the fourth stroke. So that there is a W from the 0 to 1, W from 1 to 2, W from 2 to 3, and the W from 3 to 4. However, these two terms are from the quasi-static isothermal stroke. Therefore, it is deterministic. Therefore, it doesn't contribute to the fluctuation, work fluctuation. So we have only these two contributions. These two strokes are quasi-static adiabatic stroke. Therefore, work, for example, work from 1 to 2 is given by the energy difference between the initial and the final state. And then using the reversibility condition, E1 and the E2 have this relation. Therefore, plug in this reversibility condition, we obtain this relation. Also for the stroke 3 to 4, we have obtained a similar relation. And then plug in these two, we finally obtain delta W equals to this. Okay. So now we have the delta W and the delta Q like this. the important point now is actually that E0, 0 is the initial point, and the 4 is a final point, and then they are same point. Of course, as a random variable, they are different value. They take a different value. However, after take the statistical average, this gives the same result. Namely, these are statistically equivalent. Therefore, this factor actually cancel out by taking the rate. And then finally, only this 1 minus TC over TH, Carnot efficiency factor, survive. And then we obtain this result. Okay. So now I want to explain the universal bound for this quantity. For this purpose, we consider the following 4 kinds of processes. So the isothermal, quasi-static isothermal processes, quasi-static adiabatic processes, expansion and compression, expansion and compression. These processes has been already explained. We also additionally consider isochoric processes. So the isochoric means the volume is fixed, so the lambda is fixed. Therefore, in the case of the hot isochore, we have the just vertical upward direction. And then cold isochore, we have the vertically downward direction. We also consider isobaric processes. And then expansion goes to right upward, and then compression is like left downward. Maybe I need to explain briefly what is a quasi-static adiabatic isobaric processes can be, what kind of processes. So in this work, isobaric process means a generalized pressure, which is defined like this, is constant. Namely, the effect of the variation of the lambda is compensated by the heat exchange with the bath, so that P, this generalized pressure, does not change. So this kind of situation can be, for example, realized in the following setting. So here we have the heat bath, and then we have the engine, and then now we consider some quasi-adiabatic wall. So the heat insulator, but this heat insulation is not perfect. In this case, actually there are 2 time scales. So the one time scale is a T conduction. So the heat conduction time scale from the hot heat bath and the working substance. And then another time scale is a thermalization time scale for this working substance. And then by surrounding with the quasi-adiabatic wall, this heat conduction time scale, tau conduction, is much bigger compared to the thermalization time scale. Therefore, we can think that even though there is some heat input and outgo between heat exchange between the heat bath and the working substance, this working substance is basically in equilibrium. And then under this situation, we can change the lambda with keeping P constant. For example, by taking the substance whose with the number of states is given like this, so the particle trapped in the harmonic oscillator or particle trapped in the box potential can fall into this category. And then we can actually calculate P as this expression. So that we can actually, by changing the T and the lambda such that P is constant, and then we can realize that this isobaric processes which we defined in the above way. Okay. So now we consider the 4 processes, and then here we show the table for the work fluctuation and the heat fluctuation for each type of strokes. So let's look at the work fluctuation. The isothermal process is work fluctuation is 0, and then actually the isobaric process is work fluctuation is 0 according to the same reason as the isothermal case. Isochoric process, by definition, work fluctuation is 0 because there is no work. And the only adiabatic stroke can contribute to the work fluctuation. On the other hand, in the case of the heat fluctuation, all the heat exchanging stroke, except for the adiabatic stroke, they contribute to the heat fluctuation. So the adiabatic stroke is rather special kinds of stroke, such that this is the only stroke which contributes to the work fluctuation, but doesn't contribute to the heat fluctuation. So that by noting this special property of the adiabatic stroke, actually we can show this bound, namely this quantity for the quasi-static cycle is actually maximized for the Carnot cycle. So due to the time limitation, I will not explain detail of the proof now, but if you are interested in, I can explain later in the discussion time, remaining discussion time. But anyway, we can show these quantities are maximized for the Carnot cycle. So at the end, finally, I would like to briefly explain the application of this result. So let's focus on the eta 2. Eta 2 is defined by the fluctuation of the ratio of the work fluctuation and the heat fluctuation from the hot heat bath. And then it is bounded by the Carnot case. This eta C2 equals to the Carnot efficiency to the power of 2. And then from this result, actually, we can obtain some new guiding principle to optimize fluctuations in small heat engines. First, it is rather instructive to rewrite this relation into this form. So that from this form, we can see that to reduce the fluctuation of the work output, which is actually important quantity for the practical point of view, to reduce this guy, fluctuation of the heat from the hot heat bath should be reduced. For example, if we consider the Carnot cycle, the work average of the work and the heat input is related by the Carnot efficiency, and then work fluctuation and the heat fluctuation is related to the Carnot efficiency. And then actually using this relation, we can reduce the work fluctuation, but keeping the average work unchanged. So this is nice. How to do? We can use the different type of potential. For example, by using a box potential instead of the harmonic oscillator potential, then we can reduce this guy, but keeping this average of the work amount unchanged. Namely, the working substance of these two types, say box potential or the harmonic oscillator potential, can be given by this number of states. And then actually alpha is different. F lambda is also different. But the average of the heat, actually, for this type of the working substance, average of the heat input only depends on the F of lambda, not depends on the alpha. But on the other hand, variance of the heat input, delta QH squared, this only depends on the alpha. So that this alpha, if I take the box potential or harmonic oscillator potential, alpha value is different. But the lambda is basically box potential is box size, and the harmonic oscillator length is lambda for the harmonic oscillator potential is a oscillator length. So that in the case of the box potential, alpha is 1/2, and the harmonic oscillator is 1. Therefore, I can use smaller alpha box potential, and then I can reduce this one. But I can keep this heat average of the heat unchanged by tuning lambda 1 and lambda 0. So that therefore, we can reduce the heat fluctuation, but keeping the, say, average of work output unchanged. Okay. So let me summarize my talk. So that we study the fluctuation of the performance of small classical engines, and then we found the universal relations of the fluctuation in small Carnot cycle. So that this is a relation. So that this eta n, which is defined by the work fluctuation over heat input from the hot heat bath, fluctuation of this heat input, is given by the Carnot efficiency to the power of n. And then the ratio between the work fluctuation and the total heat input, fluctuation of the total heat input, is given like this. And then we didn't explain the proof, but actually we have shown that this eta 2 and the xi 2 for the Carnot cycle is maximum among the quasi-static cycle. And then we have present this result actually provide a new guiding principle to optimizing the fluctuation in small heat engines. Namely, that we can reduce the fluctuation of the heat work output, but keeping the average of the work output unchanged. So this is my talk, and thank you for attention.
Thank you very much, Gentaro. There's a question already from Marty, so Marty, jump in.
Yes, hello, good morning. Thanks for
Good
the
morning.
talk. It was very interesting.
Thank you.
Something I was wondering is, so you find the upper bound, no, on the...
Yes.
But because you say universal, but if I think, for example, now that I go to finite time, so then so if I look at the variance, for example, so I know that the work fluctuations, they will increase. The heat fluctuations, they might increase as well. And naively, I would expect they will increase by a similar amount because you have the fluctuation dissipation relation. So then I'm not sure if you would get a lower value. Sorry.
Oh, you are totally right. So that this bound is only applicable for the quasi-static limit. Yeah. If we go to the finite time, then this is not the upper bound.
Okay.
So that if we consider all the class of the quasi-static cycle, then this bound is, this is a bound. Yeah. But if we consider finite time, then it is not the case. Yeah.
Okay. Yeah. Perfect. Thanks a lot.
Yeah. But this result can be, how can I say? The first result, universal relation, can be useful to discuss the, finite time scale case, because if we perform the end-reversible approximation, and then this result can be used for the kind of finite time thermodynamics. Yeah.
Yes, I see. Thank you.
John Greg?
My daughter.
Yeah.
Okay. Thanks.
Hi. Thank you for the talk. It was really interesting. If I understand correctly, there's no work fluctuation in other processes like isobaric or isochoric, right? So I think when we avoid adiabatic process and use them instead, we will get like zero fluctuation in the work. And I was wondering what that means, or like what is it? Is it like advantageous for engines or not?
So that you want to say that you want to close the cycle without this.
Yeah.
But this is unfortunately impossible, because isobaric process only goes up, goes down this way, and then the isothermal process like this. So let's see. Let's see. This there. sorry, you want to say that removing this? Oh no, then fine. But yeah, still our result holds because this becomes smaller. Yeah, sorry. Yeah. Our result is this is the upper bound. Yeah, so we can actually construct the say heat engine without adiabatic stroke, and then the work fluctuation equals 0. This is possible. Yes.
Yeah, I was wondering, like work fluctuation to be 0 is quite exceptional, right? So what does it mean, like in the performance of the engine, or like physically, intuitively, what does it mean in the engine operation?
Does this? I'm not really sure what you want to ask.
As far as I understand, you want to reduce the fluctuation, like the ratio of the fluctuation, right? You described it in like later slides with this box potential.
This is for example, for a Carnot cycle.
Yeah, and I think you want to reduce this value. And my question was that we actually have some scenarios where we can make this to be 0. And does that mean anything, or?
Yeah, if you just focus on the say fluctuation, this is one way, but the efficiency would be worse. So that if we take the Carnot cycle, then the efficiency is the highest, and then we can still reduce the fluctuation. Of course, we can consider some other type of cycle without adiabatic stroke. Work fluctuation is 0, but the efficiency is lower. So yeah, so if we just focus on the work fluctuation, this is fine, but you will lose something other.
Yeah, I see. Thank you.
I see. Fantastic. So any more questions? Marty, please go ahead.
Yeah, I have another question. Maybe you replied already, but can you have a cycle without work fluctuations that yields useful work?
Oh, so this is possible. This is possible. For example, the Stirling cycle, or let's see. So the Stirling cycle, this case, we have the isochoric stroke and then the isothermal stroke. No? But in this case, actually, work fluctuation equals to 0 in the quasi-static limit. But of course, efficiency is lower than the Carnot efficiency. So regarding the work fluctuation wise, it is nice, but you will lose something other.
And then the heat fluctuations here will also be 0, or?
No, there is a heat fluctuation.
Okay, interesting. Thanks. Because, yeah, okay, I wanted to understand it better. Thank you.
Because say there is an endpoint anyways. Yeah. So
it's continuous, no? Somehow and like in the Carnot cycle, you get fluctuations in heat because you disconnect it from the bath. But here, is it always connected to the bath? Yeah, okay,
maybe the Otto cycle is a better example of such a process.
But the Otto cycle, there is a work fluctuation because there is a quasi-static adiabatics.
Okay, yes, they have the work fluctuation.
So that they contribute.
Yeah.
Matthew has a question.
Yes. Thanks for the talk. I was just wondering, so in the quantities that shown on the top of this slide, is there a reason why you calculate like the quotient of averages instead of the average of quotients? You see
so if I take the rate average of the rate, then it will go to basically looking at this quantity. Yeah, but this quantity, it's not so trivial, actually. We cannot get the universal relation. That's why we focus on another type of quantity. And then, by looking at this, we could manage to get some universal relation and the bound. Yeah. So there is some motive to consider this one. Yeah, but this is totally fine. But our strategy is we focus by focusing on this, and then we can get the universal result.
So also for eta, I know you derive a relation that for like higher order, I guess moments, right?
Yeah.
But, so are there a situation where those higher order moments become important to look at, or like what situations would those higher order terms?
Higher order means third order, fourth order.
Yeah.
Could be, it might be interesting question. At present, I do not have very concrete idea. Yeah. It is cubed is a kind of skewness of the distribution, and at present I do not have very how can I say convincing setting point, but it might be interesting. Yeah, at present I do not know.
Thank you.
Sorry.
And I think Jedong had a question, please.
Okay, well, thank you for the nice talk. And
thank you.
I think recently people have been studying so-called the thermodynamic uncertainty relation, which puts some bound on the fluctuations of thermodynamic current in regard to the total entropy production. Here you are interested in the fluctuation, but I don't see any entropy contribution in this in your calculation. So can you comment something in that respect? I mean, in the context of uncertainty relation.
Yeah, actually, I was also thinking about this relation. I mean, connection. So the first thermodynamic uncertainty relation, standard one, usually consider the so-called, how can I say, steady state heat engine, not the stroke type heat engine. So the steady state heat engine definition of the work is different, which is pointed by the Horvath or Rafa. So because in the case of the steady state heat engine, transition actually can be counted as a work. If I have the two level, and then if the level changes from one to excited state to ground state, this actually can be regarded as a work sort of, and then we have the photon outside. We do not, even though we do not change the parameter, this is a work. But on the other hand, stroke engine, this kind of level transition or state change is not work unless we change the parameter.
Okay.
Yeah, so the standard type of the thermodynamic uncertainty relation is not applicable for the stroke type engine. But I saw recently there is some extended or generalized thermodynamic uncertainty relation, which take account of this work due to the parameter change. Yeah. In that case, actually, their entropy production is not so easy to calculate. Therefore, they basically consider the two-level system or that kind of thing, because they need the transition rate for between each microstate and so on, which is really hard for the continuum model. And then, but their type, relation is a kind of complementary of our relation. Yeah, so that it's not, it's a different type of the relation. Yeah, I would say.
Okay, then just one quick question. Do you have some entropy production in this engine cycle, in this quasi-static cycle?
How can I say? We do not consider explicitly, and then basically. Actually, this does there is, because, for example, we have the isochoric process, and then this simply increases the entropy.
Oh, okay.
Yeah.
Okay.
Yeah.
Thank you. Yes.
Okay, very good. Can I request the next speaker, Mark, to set up while there was one hand up which went down. I just want to make sure. Prasanna, have you withdrawn your question or?
Oh no, yeah, it's just exactly what Gentaro was saying in the end, that there are these speakers on two-level system, two-stroke engines. You can still do some kind of TURs, I think. Yeah.
Yeah.
Okay, very good. So if there are no more questions, let's all thank Gentaro for this great talk.
Thank you.
And thank you very much, Gentaro. And Mark, may